11, the development of the early atomic model. Now, for this lesson, it's a little bit different. If you look, there's not going to be any math, which some of you might appreciate. There's just some important figures, and what you're going to do is just jot down some notes about what each figure did that helped the development of the atomic model. So you can mention what it was they discovered and what that did for the progression of the atomic model. So I'm actually not going to go back here and go through this. You can just jot these down as we go through these slides together. So we begin with the ancient Greeks, and there was a philosopher, Democritus, and so he used the term atomos to describe the smallest particles of matter. So really chemistry started as a philosophical principle, as an idea that all matter is made up of small particles. And then during the medieval eras, the belief that matter was made up of atoms, it existed, but was not necessarily widespread. And then in the 17th and 18th centuries, scientists began to investigate the makeup of matter, and they discovered that there's a set ratio for the masses of elements in any given compound. So, for example, if you have 9 grams of water, you can count on 8 of those grams being oxygen and 1 of those grams being hydrogen. So if you double the sample and have 18 grams of water, then the oxygen would double and go from 8 to 16, and then the hydrogen would double and go from 1 to 2. So the ratio is always going to be 8 parts oxygen for every 1 part hydrogen. And so they started discovering that every time you have water, you can count on the mass of oxygen being 8 times that of the mass of hydrogen. So they started noticing that in different compounds, you could expect a reliable ratio. So then, and that was a law that scientists accepted called the law of definite composition, which is this idea that every compound is formed of elements combined in specific ratios by mass that are unique for that compound. So we get to a guy named John Dalton, who was actually an English school teacher, and what he did is he took the law of definite composition, so this idea that not only do we know that matter is made up of small particles, but that those particles come in ratios you can predict. And then also the law of conservation of matter, which tells us that matter doesn't get created or destroyed, it just gets converted from one form to another. And this allowed him to make an atomic model that compared the weights of elements. So Dalton's model, the first model we're going to have here, you will put what your first thing will be what Democritus did about this idea of atoms. But the first actual model is Dalton's model, and it's based on the sizes of elements and compounds. So Democritus could say that everything's made up of small particles. Dalton's the first that says these particles are going to have different sizes. Then we get the Thomson's model. And J.J. Thomson, he created the technology that allowed us to discover electrons. And with that, we upgraded Thomson's model, which is Dalton's model, but it also accounts for the presence of electrons. So now we go from thinking that matter is made up of just small particles. Then we know that they're small particles with different masses. Now we know that they also have something called electrons on them. Then we go from there to Rutherford's model. And what Rutherford discovered is that atoms are actually made up of mostly empty space with a small nucleus inside of it. So then Rutherford's model is based on the empty space and the nucleus inside of an atom. So now not only do we know that atoms have different masses, we know that they have electrons, we also realize their structure is mainly empty space with a nucleus in the center. Then we have Chadwick's model, and Chadwick's model is based on the discovery of neutrons. So we find out that on top of everything else we've discovered, there are also neutrons inside of an atom. And then we have a guy by the name of Niels Bohr, and Niels Bohr was studying electrons, and he suggested an idea. You actually might recognize this name from physical science. In some physical science classes, you end up making Bohr's models, so you actually draw demonstrations of this model. But what he did is he took a mathematical model, and he predicted that as electrons gain energy, they would place themselves in different energy levels. So the Bohr's models almost look like rings that keep on going further and further out. And the idea is that the electrons can be predictably placed in those different rings. So Bohr's model is based on the energy levels of electrons. What physicists did with these energy levels is they quantized them. And when something is quantized, it means that you assign numbers to it. So you could say that like the classrooms in a school are quantized because they are given numbers. Um, for example, if you're going to room 19, that doesn't mean it's because there's 19 people in that room. It's the 19th room that was named. It's no different than room number one in a lot of cases. It was named later on. And then the last model, the quantum model, I had these guys together because their two discoveries were, when combined, are what we did to upgrade the Bohr's model. So first we have de Broglie, who came up with this idea called de Broglie wavelengths, and this is the idea that electrons are particles that actually act like waves. So they're not just little dots just floating; they actually behave like waves. And then we have a guy named Heisenberg who the idea with this Heisenberg uncertainty principle that we're about to bring up. I want you to imagine placing a dot on like a ceiling fan. If you place a dot on one of the whatever they're called, the little arms of the ceiling fan, then if I turn the ceiling fan on high, that dot is going to be just like, if it's a blue dot on a white ceiling fan, you'll just see this blue circle as this dot's moving so fast you can't ever see it. So at that moment, you know how fast it's moving, but you can never tell me exactly where it's at because it blurs. Or if you take a picture, well, when you take the picture, it freezes everything. So you can tell me at that moment where exactly the dot is, but since it's frozen in time, you cannot tell me how fast it's moving. This is the same kind of idea that Heisenberg, basically, he said we cannot know the energy and the location of an electron. And so with the idea that they act like waves and that they are so unpredictable, we cannot tell you both the energy and location at the same time. The mathematical Bohr's models that have these nice little rings and where each one is supposed to be at, that doesn't quite work when they act like waves and they're super unpredictable. So we had to upgrade to what's called the quantum model, where instead of putting them in these little orbits or these perfect little rings that Bohr had drawn, the quantum model puts them in orbitals, which is a three-dimensional region of probable position. So really, basically, you can say that with de Broglie and Heisenberg, they upgraded the Bohr model to account for the fact that electrons have very uncertain behaviors. So that's everything here. You have access to this PowerPoint, so you can go through it if need be. And as always, email me if you have any questions.